Let me start with a strange paradox. Give a modern large language model a complicated software problem, and it can sometimes understand the architecture, write hundreds of lines of code, explain the logic, find bugs, refactor the design, and even build an entire application. But then ask it to multiply 48,372 by 71,946, and suddenly this incredibly sophisticated system can give you a completely wrong answer. Why? Isn't multiplication much easier than writing software? And more importantly, what does this tell us about what an AI like an LLM actually is? To understand this, we first need to separate something that we often mix together: language, reasoning, and computation. When we see an AI producing a correct mathematical answer, it is very tempting to imagine that somewhere inside the model there is a little calculator performing the calculation. But that's not really how a language model fundamentally works. A large language model is trained to predict sequences of tokens. It sees enormous amounts of text, code, formulas, examples, explanations, conversations, and patterns, and gradually learns statistical relationships between them. So when you ask a model a question, its fundamental mechanism is not, what operation should I execute on these numbers? Its fundamental mechanism is much closer to, given everything I have learned and everything that came before, what tokens are most likely to come next? That sounds like a subtle distinction, but it explains a huge amount about both the strengths and weaknesses of LLMs. Imagine I ask you to finish this sentence. The capital of France is... You don't calculate anything. You retrieve a deeply learned association, Paris. Now imagine I ask, explain why software systems use caching. Again, you don't perform an exact numerical operation. You organize concepts you've learned. You recognize familiar patterns. You connect ideas. You construct an explanation. Now consider a 5-digit multiplication problem. 48,372 times 71,946. There are no semantic patterns that can simply be recalled to guarantee the answer. You have to perform a sequence of exact operations. You need to multiply individual digits, manage carries, maintain intermediate values, align place values, and combine the results without making a single mistake. One wrong digit in one intermediate step can destroy the final answer. This reveals the first deep difference. Language is highly redundant and approximate. Arithmetic is highly constrained and exact. There are many ways to explain an idea correctly. There is only one correct result for a multiplication problem. You can explain gravity in 10 different ways and still communicate the same concept. But if the answer to a calculation is 3,482,917, then 3,482,918 isn't almost correct. It is simply wrong. That difference matters enormously for systems like language models, because language itself is full of flexibility. Suppose I say, the dog ran quickly across the street. You could rewrite it as, the dog sprinted across the road, or the dog moved rapidly from one side of the street to the other. Different words, different sentence structures, same basic idea. Language contains many acceptable outputs. Arithmetic does not. 2 plus 2 is not 5 because 5 sounds plausible. And that is one reason humans also struggle with large calculations when we try to do them entirely inside our heads. This is actually a useful reality check. Sometimes we look at an AI making an arithmetic mistake and think, how can something this intelligent fail at multiplication? But human intelligence has exactly the same kind of boundary. Most people cannot reliably multiply two 5-digit numbers mentally, and that's not because humans are unintelligent. It is because our brains were not designed to function as arbitrary precision calculators. We evolved to estimate quantity, recognize objects, understand social interactions, navigate environments, remember important experiences, and reason about the physical world. We did not evolve to internally execute thousands of precise arithmetic operations. So what did humans do? We invented tools. First, we developed arithmetic procedures, then writing, then mathematical notation, then tables, then mechanical calculators, then electronic calculators, then computers. This progression contains a very important idea. Human intelligence has never been purely about what happens inside the brain. Human civilization is built around extending cognition beyond the brain. A book is external memory. A calculator is external arithmetic. A map is external spatial memory. A spreadsheet is external structured computation. A computer is external programmable reasoning and execution. In a sense, civilization itself is a giant cognitive tool system, and this gives us a much better way to think about LLMs. Maybe the question should not be, why can't the model do everything itself? Maybe the better question is, what kind of cognitive work is the model naturally good at? And this is where software becomes especially interesting, because software sits at the intersection between language and computation. Code is extremely precise, but code is also highly structured. And that structure is exactly what language models are extraordinarily good at learning. Think about a typical programming task. You ask, create a function that takes a list of numbers and returns the largest value. The model has seen patterns like this countless times. It knows programming syntax, it knows loops, it knows conditional statements, it knows function definitions, it knows common algorithms, it knows naming conventions, it knows what errors programmers usually make, it knows how APIs are typically used, it knows common architectural patterns. It knows what a test suite looks like. It knows what documentation looks like. In other words, software contains a gigantic amount of regularity, and LLMs are incredibly good at modeling regularity. That's why they can appear almost magical when writing code. But here's the subtle part. When an LLM writes a program that calculates the product of two huge numbers, the model does not necessarily need to perform the multiplication itself. It can write, return a perch b. And now a real computational system, the programming language runtime, or the processor, does the exact calculation. The model generated the instructions. The machine performed the computation. This distinction is incredibly important. The model is often acting as the architect, translator, planner, debugger, or programmer. The computer remains the calculator. And once you see that distinction, a lot of modern AI starts making more sense. When an AI coding agent generates a database query, it may not actually execute that query itself. It generates the SQL. The database executes it. When it writes Python code, it may not internally simulate every CPU instruction. Python executes the code. When it uses a calculator tool, the calculator performs the arithmetic. When it calls a search engine, the search engine retrieves the information. When it opens a file, some external system provides the contents. The intelligence is increasingly not just inside the model, it is in the interaction between the model and the tools around it. And this leads to a much deeper idea. A modern AI system is beginning to look less like a single brain and more like a cognitive system. The language model is one component, memory is another, tools are another, execution environments are another, search is another, databases are another. And the model's job is increasingly to coordinate all of them. This is what makes AI agents so interesting. An agent does not need to know everything. It needs to know when it does not know something. It does not need to perform every calculation. It needs to know when calculation should be delegated. It doesn't need to memorize every document. It can retrieve information from external memory. It doesn't need to manually inspect every line of a huge data set. It can write code to analyze it. This is actually very similar to how good human problem solving works. Imagine a professional engineer. Suppose they need to perform a complicated calculation. Do they spend 20 minutes doing long multiplication by hand? Probably not. They use a calculator. Suppose they need information from a document they haven't read in 6 months. Do they rely entirely on memory? Probably not. They search the document. Suppose they need to process 10 million rows of data. Do they manually inspect every row? Obviously not. They write a program. So expertise isn't necessarily the ability to perform every task directly. Expertise often means knowing which mechanism should handle which task, and that brings us to something philosophical. We often define intelligence as the ability to solve problems, but maybe that's too simplistic. Perhaps intelligence is also the ability to construct a system in which problems can be solved efficiently. Think about a chess grandmaster. The grandmaster doesn't memorize every possible future move. They use patterns, they recognize positions, they identify strategies. They calculate only where calculation matters. The same principle appears in science. A scientist doesn't keep every piece of scientific knowledge in their head. They use papers, they use instruments, they use mathematical software, they use simulations, they collaborate with other people. No serious scientist tries to become a human database, calculator, microscope, and supercomputer at the same time. So perhaps we're making a conceptual mistake when we look at LLMs and demand that the model itself should be the complete computer. A language model is a component, and components have strengths. A CPU is good at exact computation. A GPU is good at parallel numerical operations. A database is good at structured retrieval. A search engine is good at finding information across huge collections. A language model is extremely good at modeling language and patterns. The interesting engineering challenge is combining these capabilities. This is why tool use is such a fundamental part of modern AI. Suppose I ask an AI, what is 18,937 multiplied by 72,841? A weak system might try to generate the answer directly. A better system might think, this is an exact arithmetic task. I shouldn't trust my internal approximation. I'll use a calculator. That is not a failure of intelligence. It is arguably a sign of better intelligence, because the system recognized the nature of the problem. And this distinction between reasoning and computation becomes even more interesting when we consider software engineering. A model can write a sorting algorithm, but whether that algorithm actually behaves correctly on millions of inputs is something execution can test. The model proposes, the machine executes, the tests verify, the feedback improves the next attempt. That creates a loop, and increasingly, modern AI systems are built around exactly this loop: reason, act, observe, correct, try again. Instead of expecting the model to internally simulate the entire world, we allow the model to interact with the world. That is a major shift, and maybe this is where our intuition about intelligence needs to change. For decades, we imagined AI as a giant artificial brain, something that simply becomes smarter and smarter until eventually it can do everything. But the emerging picture may be different. It may not be one giant brain. It may be a system of specialized capabilities, coordinated by a general reasoning interface. The language model becomes the layer that communicates, plans, interprets, and orchestrates. Tools provide exact capabilities, external systems provide memory, execution environments provide reality, and feedback provides correction. In that sense, the real breakthrough may not be making the model perfect at everything. It may be making the model extremely good at knowing what should happen next. There is another fascinating consequence of this. We often criticize AI for making simple mistakes, and some of those criticisms are completely justified, but a mistake can tell us something about the architecture of intelligence. For example, imagine an AI that writes a sophisticated program but makes a basic arithmetic mistake. That tells us its competence is not a single scale. Intelligence isn't a ladder where every capability increases together. A system can be extraordinary at one form of abstraction and surprisingly weak at another. Humans are exactly like this. Someone can write beautiful poetry and struggle with algebra. Someone can perform incredible surgery and be terrible at public speaking. Someone can understand advanced physics and still forget where they put their keys. Human intelligence is not one uniform ability. It is a collection of specialized capabilities operating together. LLMs are revealing this in a particularly dramatic way. They can produce language that sounds deeply intelligent. They can manipulate concepts. They can write code. They can summarize documents. They can reason about complex scenarios, and yet they can still fail at tasks that appear trivial to us. That's not necessarily a contradiction. It's a reminder that the appearance of intelligence and the mechanism producing it are not the same thing. And perhaps this is the biggest lesson. When you ask an LLM to calculate something, you shouldn't just ask, does it know math? You should ask, what kind of mathematics is being required? Is it recognizing a mathematical pattern, explaining a concept, deriving a formula, applying an algorithm, or executing a long sequence of exact numerical operations? Those are very different tasks. An LLM may be excellent at explaining why multiplication works. It may be excellent at writing a program that performs multiplication. It may even be excellent at designing a system that handles millions of calculations. But that doesn't automatically mean it should perform every multiplication internally, and humans aren't fundamentally different. We didn't become more intelligent by memorizing every calculation. We became more capable by building tools. The calculator didn't make humans less intelligent. It increased what humans could accomplish. The computer didn't eliminate human thinking. It amplified it. The internet didn't put every piece of knowledge into our brains. It gave us external access to enormous amounts of knowledge. And AI tools may represent the next stage of that same process. Maybe the important question isn't, will AI become smart enough to do everything? Maybe the more interesting question is, how powerful can intelligence become when it learns to combine reasoning with tools? Because the moment a system can reason about a problem, identify its own limitations, choose the right external tool, interpret the result, and continue reasoning from that result, something fundamentally different happens. The model stops being just a predictor of text. It starts becoming part of a larger computational process. And that brings us back to our original 5-digit multiplication problem. Why can't the LLM just calculate it? Sometimes it can. Sometimes it will get it right. But the deeper point is that getting the right answer internally isn't necessarily the most important capability. The important capability is recognizing, this is an exact computation. There is a better machine for this. I know how to use it. That sentence may sound simple, but philosophically it represents a very deep idea. Intelligence is not the absence of limitations. Intelligence is the ability to work effectively despite limitations. Humans have always done this. We extend memory with books. We extend vision with microscopes. We extend calculation with mathematics and machines. We extend communication with language. And now, we are building systems that extend reasoning with language models and tools, so perhaps the future of AI isn't a machine that becomes a perfect replacement for every other machine. Perhaps it is a machine that becomes incredibly good at coordinating them. A calculator is better at calculating. A database is better at searching structured information. A compiler is better at executing code. A computer is better at performing exact operations. And a language model may be particularly good at connecting all of these things together through abstraction, communication, and planning. That is why a model can appear bad at something as simple as multiplication while being remarkably good at software engineering. Because software engineering is not just calculation, it is understanding intent, recognizing patterns, choosing abstractions, connecting components, writing instructions, handling ambiguity, communicating ideas, and then, crucially, knowing when to let another machine handle the exact work. The future may therefore belong not to systems that can do everything internally, but to systems that can intelligently distribute work across the right tools, and that may actually bring AI closer to human intelligence, not farther away. Because human intelligence has always been less about doing everything ourselves and more about knowing what we can do, what we cannot do, what tools can help us, and how to bring all of those capabilities together. Maybe the smartest system isn't the one that can calculate everything. Maybe it's the one that knows when it shouldn't calculate at all. That's all for today in Dots and Arrows. Thanks for watching.